Hey, this is a video for 6.1. It's actually the second half, and we're going to take a closer look at discrete numerical variables in this one. So we primarily focused on continuous numerical variables when we did it 6.1 the first time. All right, so a reminder, in Chapter 1 we classified variables as either numerical, such as ages, or categorical, for instance, if the coin land heads or tails. There's a little bit of a typo there. In this chapter, we need to further break the numerical variables down into two more categories, discrete variables and continuous variables. So what we saw earlier was that discrete variables or discrete outcomes have numerical values that you can list or count, and continuous variables or continuous outcomes have numerical values that cannot be listed or counted because they occur over a range. So in picture form, remember we had the steps to represent the discrete variables, and continuous was the ramp. All right, so number 2, we're going to take a closer look at discrete variables in this section. Following are two examples of discrete variables. So 1, whether a coin lands heads, if the outcomes are coded as 0 or 1. Remember, reminder here that 1 represents a success, and in this case we're going to call that heads. Could be called tails in another example, but in this example we're going to call it heads. So 1 is heads, and that means 0 is tails. Or you could think of it as not heads. All right, and the result of rolling a fair die is another example. And in this case, the outcomes are 1, 2, 3, 4, 5, and 6. And fair means that all 6 of these outcomes are equally likely. If they weren't fair, then we might have one of these outcomes occurring more often than the others. Right, number 3, the following is the probability distribution for flipping a fair coin. Notice that this distribution shows the two possible outcomes. We've got heads and tails, as well as the probability of each outcome. And since the coin is fair, the probability of heads is 0.5, and the probability of tails is also 0.5. This probability distribution can be shown in either of the forms given below. We've got the bar graph here on the left, so notice that it's labeled with relative frequency. And the probability of getting heads equal to 0, which is another way of saying tails, is 0.5. And the probability of getting heads is also 0.5. Right, so that's our bar graph. That's one way to display this probability distribution. And the other way, over here on the right, we also have another graph. It's not a bar graph. They're just using line segments. So notice this line segment above 0. The height is still giving us the probability. In this case, our vertical axis is labeled as a probability. Right, so it's the same vertical scale. They both go from 0 to 0.5. We just renamed it with probability here. And again, instead of bars, we just have these line segments indicating the probability. And if we look more closely on the horizontal axes, we still have that coding. Again, where 0 is tails, or you can think about it as not heads. You didn't get a head when you flipped the coin. And 1 is heads. All right. Moving on, probability distributions can also be given in table form. The table for the above probability distribution is given below. Notice that this table also tells us all the possible outcomes for flipping a coin and the probability of each outcome. So same thing we saw in the previous section. We've got our list of outcomes given, anything that can happen when you flip your coin. And we've got the probability that's associated with each of those. Okay, number 4, this probability distribution is a theoretical model of what happens when a fair coin is tossed an infinite number of times. So theoretical, think about in theory, what would happen. All right, number 5, the following is the probability distribution for rolling a fair 6-sided die. Notice that this distribution shows the 6 possible outcomes. We've got 1, 2, 3, 4, 5, and 6, so it's giving you the number on the die, as well as the probability of each outcome. Probability distribution can again be shown in either of the forms given below. So we've got your bar graph on the left, and you've got your gaps between the bars, for indicating that these are discrete values of the variable, not continuous. And the vertical axis is labeled with relative frequency, which again is the proportion of times that you would roll each number. So it looks like that's around 0.16, and if you grab a calculator and do 1 divided by 6, you're going to get that that's around 0.16 or about 0.17 if you round. And then on the right, we just rename that axis with probability. So notice the scale is the same. It goes from 0 to 0.1617, just like the one on the bar graph on the left. And the horizontal axis, same thing. We've labeled it with numbers, so the number of the roll. But instead of using bars, we're just using line segments. So it's the height of the line segment that tells us the probability of each of these outcomes. Okay. All right, the table for the above probability distribution is given below. Notice that this table also tells us all of the possible outcomes for rolling a fair six-sided die and the probability of each outcome. So right here we can confirm that 1 out of 6, so one number out of the 6 possible, is about 0.17 or 0.167 if we want to be more exact. All right, so again, it's listing all of the outcomes, just like with the coin toss problem, and the probability of each outcome occurring. All right, so this probability distribution is a theoretical model of what would happen when a fair die is rolled an infinite number of times. Okay, so number 6, does a theoretical model do a good job of predicting what will happen if we actually roll a die 1,000 times? So I used StatCrunch to run a simulation, since I didn't feel like rolling a die 1,000 times. The results of the simulation are shown below. Okay, so we've got, on the left, we've got the frequency, which is just another way of saying count. So this is telling you number of times that each roll appeared, or each number appeared. So for instance, it looks like the number 1 appeared about maybe around 155, 160 times. And the number 2 appeared just about the same number of times, maybe a little bit more. And then on the on the right, notice we rescaled that axis to give us a relative frequencies. So for instance, this number, 0.15, is the result of taking 150 outcomes and dividing it by the 1,000 rolls that we did. So in this vertical scale on the right has just been rescaled from what's over here on the bar graph on the left. The horizontal axis, though, is the same. So the sum of one roll is just saying you roll it once, what number did you get? So we could cross out sum if we wanted to. Same thing over here. We could just say here's the result of one roll. All right, the frequency table that goes with this simulation. So again, keep in mind that this is all from a simulation. These are the results of a simulation in your graphs up above. And this table is also giving you the simulation results. So not theoretical, not what would happen in theory, but what actually happened when I rolled the die 1,000 times with the applet. All right, so we can see, it looks like the 5 appeared the most when we did the simulation. And notice that the bar above 5 is the tallest in our graphs above. All right, so according to the simulation, what's the probability of rolling a 3? So we want to know what's the probability that we get a roll equal to 3. So we could say that's the same thing as what's the probability that x is 3. Just use x as our variable to represent our variable. And according to the simulation, we look at our row for 3. That happened 0.168 or 16.8% of the rolls in our simulation. So it must be 168 out of 1,000. Okay, so the second one, according to the theoretical model, so in theory what would happen, what is the probability of rolling a 3? In theory, you should get this the same number of times, or same frequency as all the other rolls. So this should happen 1/6 of the time, and that's about 16.7% of the time. So the last question then, did the model accurately predict what would happen in the simulation? We can say yes. The model's value, 16.7%, the theoretical model, is about the same as what we got in our simulation.